Hi, my name is Cody, and today we're going to talk about inner products, norms, and their relationship. Going over the definitions, let's say we have a vector space V over a field F. Well, an inner product on V is then going to be a map from V cross V to the field such that the following three conditions are met. The first condition is positive definite, which states that the inner product of V with itself is always going to be non-negative and is only going to be zero when the vector in question is the zero vector. Condition 2 is conjugate symmetry, which states that the inner product of V with W is going to be equal to the conjugate of the inner product of W with V. And condition 3 is just linearity in the first argument. On the other hand, a norm on a vector space is a function from the vector space to the interval 0 to infinity, and it also satisfies three conditions. You'll notice that the first condition looks almost analogous to the inner product version, whereas condition 2 says that if you have the norm of a scalar multiple of V, you can pull out the modulus of the scalar. And the third condition is the familiar triangle inequality. So now that we have the definition for both an inner product and a norm, we can talk about the Cauchy-Schwarz inequality, which is an important relationship between the two. So it basically says that if you have an inner product space, and let's say two vectors u and v, the modulus of the inner product of u and v is going to be less than or equal to the product of the norms of u and v. And this is going to be an equality only when u and v are linearly dependent. So an important consequence to this would be, let's say that we have some inner product on a vector space V. And for the purposes of this video, let's assume that V is either a real or complex vector space. So we can actually go ahead and define a norm on V by setting the norm defined to be equal to the square root of the inner product of V with itself. Now we got to make sure that this is actually a valid norm, which means we got to make sure it satisfies these three conditions. Well, the first two are relatively straightforward, so we won't go through those. But the third one, which is the triangle inequality, involves the Cauchy-Schwarz inequality. So let's walk through that together. So let's pick any two vectors, u and v, in our space. We'll compute their norm squared, and by definition, that's going to be the inner product of u plus v with itself. And using linearity, we're going to get the following. Alrighty, so now we go ahead and look at this third term. We recall that the inner product is conjugate symmetric. So what we can actually go ahead and do is reverse u and v and just take the complex conjugate. So we'll take the conjugate, and now let's say we know that the inner product of u and v is going to be some complex number. Let's just call it a plus ib. Well, of course, if we do that, then the conjugate of this is just going to be a minus ib. And if we were to add these two together, we would get 2a, or 2 times the real part of the inner product of u and v. So, writing this in, we have that the norm squared is going to be equal to inner product with u and u, plus 2 times the real part of the inner product of u with v, plus the inner product of v with itself. So taking this one step further, if we were to take the modulus of the inner product of u with v, well, this is just the modulus of a plus ib, which of course is just going to be the square root of a squared plus b squared. And this, we know, is actually going to be bigger than or equal to a, since b squared is a non-negative real number. Well, if that's the case, we can make this into an inequality and write that we have this. Well, in this case, we can actually apply the Cauchy-Schwarz inequality to this middle term. And so this is going to be less than or equal to the product of the norm of u with the norm of v. And again, using the definition of our norm on these first and last terms, we're going to get that this whole thing is less than or equal to norm of u squared plus 2 times the norm of u times the norm of v plus the norm of v squared. And this is a simple quadratic that we can just write as the norm of u plus the norm of v, the whole thing squared. And as you can see, if we take the square root of both sides, we get the triangle inequality. So it's a done deal. So an important takeaway is that whenever we have an inner product, we actually get a norm on V. So a natural question to ask is, if we have a norm on V, when does there exist an inner product on V so that the norm of V is going to be equal to the inner product as we've defined it? And we will answer this question in the next video.